All right. So let's take a look at this next sheet. This little cheat sheet that I gave you to help you out. No, you will not be allowed to use the cheat sheet on your test. It is just to help you study between now and the test. We will be dealing primarily in square roots and cube roots. However, our other ones, fourth roots, fifth roots, they do end up showing up from time to time. So we do have to know how to handle them. But again, we will stick primarily in square roots and cube roots. So this little chart, what happens right underneath the radical sign here, these are our first 10 perfect squares. You should have those memorized by this point in time. Just saying. So square root of 1 is 1. Right, there it is. 2, 3, 4, 5, 7, 8, 9, 10. So the square root is the number underneath the radical sign there. The answer is the root that you get when you take the square root of it. Over here, again, these numbers underneath, these are our first 10 perfect cubes. What do you think I'm going to tell you about those? You should memorize them. There's our first 10 perfect cubes. Perfect squares, perfect cubes, again, those are the most common ones we're going to be dealing with. You should know those ones. You should have some familiarity with your perfect fourths and those perfect fifths. Okay, so that's 1, 2, 3, 4.
It just goes from 1 to 10.
Yep. All right. Perfect squares, perfect cubes, perfect fourths, and perfect fifths. So the other thing that's going to come into play with our radicals for this unit is we're also going to have a lot more variables underneath your radical signs as well. So the bottom half of this are the perfect squares, cubes, fourths, and fifths when you have a variable involved. So in order to take the square root of an algebraic term, the exponent must be a multiple of 2. If your exponent is a multiple of 2, it is a perfect square. You're going to be able to take the square root of it. So looking at our first example, x squared, the square root of that, I would divide my 2 by 2, so I get x to the first. So when I take the square root of x to the fourth, 4 divided by 2 is going to give me x squared. The square root of x to the sixth would be x to the third. What do you think square root of x to the eighth is?
4.
And then x to the
5th.
and then to the sixth. Good job. So for our cube roots, in order to take the cube root of an algebraic expression, the exponent has to be a multiple of 3. If it is a multiple of 3, it is a perfect cube. So again, because I'm taking the cube root this time, I have to be able to divide the exponents all by 3. So for that first one, 3 divided by 3 would give me my x to the first. 6 divided by 3 would give me x squared. 9 divided by 3, 12 divided by 3, 15 divided by 3, and then 6 divided by 3. So then if you're trying to take the fourth root, what do you think it needs to be a multiple of? 4. Very good. Whatever root it is, that is what it needs to be a multiple of. So when you're taking that fourth root, you just divide those exponents by 4. So x to the first, x squared, x cubed, x to the fourth, x to the fifth, x to the sixth. And then for a fifth root, what does it have to be a multiple of? Multiple of 5. So if it were, say, like a 7th root, what would it have to be a multiple of? Very good. You see the pattern. Good job. So now if you're ever unsure of a number, whether it is a square root, cube root, 4th root, 5th root, you can check that in your calculator. So in your calculator, if you push that math button, choice 4 is your cube root. It has its own root there because, again, cube root is actually quite frequent that we end up using that one. But choice 5 lets you put any root in there. So if you got to find a 4th root, you can put a 4 in there and then see if it ends up being a 4th root. If you needed to find a 6th root, you could put a 6 in there and be able to figure it out that way as well. So let's get to it. Looking at our parts of our radicals. Yes. Yes, it is. So looking at our parts of our radicals, first we have this little letter right here, which is N. N is what we refer to as our index. N is a little subscript number. It's a little tiny number, kind of like an exponent is written as a smaller number. When we do get into our sequences and series, we'll see a lot more subscripts as well. Your index is what root are you looking for? So whatever number is there is telling you what root we're looking for. So if there's a 3, we're looking for a cube root. If there's a 5, we're looking for a 5th root. Commonly, you see no number written there. So that's just indicating it is your square root. We've seen that a lot so far already. So if there is no number out in front, it is your square root. You will see some people from time to time actually putting a 2 there. That is the other way to show it's a square root. You could put the 2 or you could leave it blank. And then your K, that is what we call your radicand. So a lot of times what we're going to be doing is we need to simplify that number down. We can't call it a perfect because most of the time it is not going to be a perfect number. It's not going to be perfect square or perfect cube or perfect 4th. So we just refer to it as our radicand. It just gets a name. Yeah.
Okay. Are there going to be any imaginary numbers?
There could be. There could be. There could. I know, you're so excited. All right, so I wrote the steps there on how to simplify radicals if they are not perfect squares, cubes, or 4th. So I find it's easier to actually just go through the process instead of sitting here and reading what the process is. So taking a look at our first one there, plus or minus the square root of x squared over 4. Whenever you have two numbers like this, easiest thing to do is to separate them and give them each their own radical sign. The square root of x squared over the square root of 4. So we are dealing with perfect squares here because there is no index number written, so that's telling me it's a square root. Is x squared a perfect square? Yeah. So square root of x squared would be x. Square root of 4 is a 2. And then I have to keep bringing down that plus minus sign that they had out in front. That's it. That was a hard no, if you didn't catch that. All right, so 100, is that a perfect square? Is x to the 4th a perfect square? And is y to the 6th a perfect square? Okay. So square root of 10. Oh, sorry, I already said it. Square root of 100 is 10. Gave you that one. You're welcome. Square root of x to the 4th is x. And square root of y to the 6th. There you go. All right, next one now we switch to cubes though. So you got to switch your mindset a little bit. We're used to the squares. We've got to go to cubes. Is 8 a perfect cube? Yes. Is x to the 3rd a perfect cube? Okay. What's cube root of 8? Cube root of x cubed. So 2x. I know I do it on purpose. I just don't write in yellow because you can't see yellow in the back. You can't see yellow.
Oh, there's a negative. Green's pretty cool. What? You skipped yellow though.
All right, next one. We're doing the cube root. So negative 27, is that a perfect cube? Yes. Cube roots, odd roots, any odd root, so 3, 5, 7, you can have negatives. Because remember, negative 3 times negative 3 times negative 3 gives you your negative 27. Odd roots can be negative. Even roots, though, give you i's. So odd roots can be negative. Even roots, if you have a negative, it's going to give you an I. So negative 27, because I'm doing cube root, we're fine. We can leave that there. X to the third, is that a perfect cube? Y to the 15th, is that a perfect cube? Yes. So we get negative 3 xy to the 5th. I will remember that. All right, what root are we looking for in number 5? Fourth root. So is 16 a perfect fourth? Yes. Is x to the 8th a perfect fourth? Y to the 12th? All right, let's do this. What's the fourth root of 16? 2. And then we have x to the y to the, there we go. All right. Which root for number 6? Fifth root, yes. Which we would get a 3. But the negative's out in front. That's okay. It doesn't do anything. It just hangs out in front. It's your little sister you brought to the store. She's still there. She doesn't go anywhere. So fifth root of 243. And then the fifth root of x to the 5th. So negative 3x. Square root, yes. Is 50 a perfect square, though? Nope. X cubed, not a perfect square. So we need to start breaking these things apart a little bit. Now, some teachers do it different ways. I like to do it where I make 2 separate radical signs and simplify that way. Some teachers do it all under one radical sign. It doesn't matter how you do it. The process is still going to be the same. So my 4 is still out in front. I'm looking at my 50. What is our largest perfect square that goes into 50? 25. And then 25 times 2 gives us our 50. So I'm just taking my 50. I'm breaking it apart. I'm going to break apart my x cubed. I can take an x squared and put it in the perfect square, and then an x to the first would stay with my 2. So I still have all 3. I've just separated them. Kind of like factoring. Yes, you're breaking them apart. So now what's the square root of 25? 5, and then times the 4 that's already out in front gives me 20. And then the square root of x squared is just x. And then 2x, because it is not a perfect square, is going to stay underneath the radical sign. So 20x radical 2x. All right, number 8. What is our largest perfect square that goes into 48? 4 is a perfect square that goes into it. It's not the largest, though. 16. And then it's 16 times 3, so 3 goes in the other one. Is x to the 4th a perfect square? Yes. Is y to the 5th a perfect square? No. So I have to find the largest multiple of 2 out of the 5 that I can get. So that's actually going to be y to the 4th. And then I'm going to put a y to the 1st. So I still have my 4 plus my 1. I still have 5. It goes in the second one. But you always want to find the largest amount that you can take out of it. So now it's the square root of 16. Square root of x to the 4th. X squared. but I'm going to multiply it by that one that was already out in front. So x cubed. And then I got y squared. That is a messy y. There you go. And then the square root of 3y. I multiplied it, so this, when I took the square root of it, became x squared, and then I multiplied it by that one, so I got x cubed now. All right, 9 is a cube root. So what is the largest perfect cube that goes into 40? 8. So this is going to be cube root of 8. And then the cube root of 5, because 8 times 5 is your 40. Cube root of 8 is 2. And then times the 2 that's already there gives me a 4. And then I got my cube root of 5. All right, 10. Negative 125. Is that a perfect cube? Yes. Negative, or x to the 7th. Is that a perfect cube? No. The largest perfect cube I could get from x to the 7th, though, would be x to the 6th. And then in that one, I'm going to have just x. So it still equals 7. I'm just separating them. So the cube root of a negative 125 is going to be negative 5. Divide our exponents. So we get x squared. And then we still have our cube root of x. Okay. Fourth root for 11 is 32, a perfect fourth. Perfect fourth, 32. No. So what is the largest perfect fourth that goes into 32? If only there was this amazing chart that Miss Pelkey gave you. 16. So x to the 7th, is that a perfect fourth? No. So the largest perfect fourth that I could pull out of there, though, is x to the 4th, leaving x to the 3rd in the other one. And then y to the 4th is a perfect fourth, so that's going to go in the first one. So the 4th root of 16 is 2. Divide my exponents, I get x to the 1st, y to the 1st. And then the 4th root of 2x cubed. Be careful on problems like these that the 4 is actually above that radical sign and it's not looking like it's an exponent on your y, because it will get marked wrong that way. So just be careful with those. 12, 32, is that a perfect fifth? Yes. Is x to the 5th a perfect fifth? Y to the 6th? No. Z to the 7th? No. Okay. So I'm going to put 32, x to the 5th, y to the what? 5th, z to the 5th, and then I'm going to have y z squared left over. So the 5th root of 32 is 2. 2xyz.
And then it's the
5th root.
And then it's
yz squared.
Oh my.
Very nice. All right. So now we'll go through our operations with our radicals. So adding and subtracting radicals. You can add and subtract radicals if they have the same index. So if they're both square roots, both cube roots, you cannot add a square root and a cube root together. So they have to have the same index. And then they also have to have the same radicand, which again, where is the radicand located? The thing, yeah. Yes, it's the number underneath the radical sign. So looking at our first example, are they all the same index? Yes. Are they all the same radicand? Negatory. So what could we do? Do what one by one? No?
Like so the 5 and 7, then the other one, like one by one.
But we're trying to add and subtract them, so.
Yeah, and then once you do them one by one, then you subtract them.
Do what one by one?
Each part. Like saying the 5 root 27. Do that and then go to the.
Do what to it?
You do what we just did.
What was that called?
Simplify.
Yeah, simplify them. See, I knew what you were talking about. I was trying to get you to say the word.
My brain was like.
You were almost there. All right, so what's our perfect square that comes out of 27? 9. Square root of 9 is, so times the 5 makes that 15, radical 3. I don't always show the middle step if it's just numerical because those ones are a little easier. I can't simplify the 4 radical 3 anymore. There is no perfect square that can come out of 3. How about for the 12? 4. Square root of 4 is 2, but times the 2 that was already there makes it a 4. So now they're all the same index. They're all the same radicand. They're all radical 3s. You add and subtract them just like you would x's. So 15 minus 4 plus 4 gives me 15 radical 3. Your radical is not going to change. You're just adding and subtracting your coefficients. (14). What is our perfect square that can come out of 18x to the third? And? I'm going to assume you meant x squared.
Oh, yeah, I did.
Yeah, okay. So 9x squared, 2x will be in the other one. What is the square root of 9x squared? 3x. But then it also has to be multiplied by that 2/3 x that was already in front of the radical. That didn't go away. It's still there. So 2/3 times 3. 2. X times x. So 2x squared radical 2. So looking at the other one, 72 actually has quite a few perfect squares that can go into it. You've always got to find the largest one. I heard somebody mumble it. 36. And then it would be x to the 4th. X to the 4th would be the largest one that we can get out of x to the 5th. So square root of 36, x to the 4th. 6x squared. Radical 2x. And I just brought down my negative because I'm subtracting here. So now we have same radicals. We can actually subtract. So 2x squared minus 6x squared. Negative 4x squared. Radical 2. Now let's just say for a second. Let's just say that that was just 2x and not 2x squared. Could I subtract 2x minus 6x squared? No, because those aren't like terms. So what you would see in this situation if this happened is they would write it like this. Because they still want to only have the one radical because they are the same. So you still have to condense it down as much as possible. This is how that condensing would end up happening, is they would put the two things in parentheses because you can't actually subtract them. with your radical sign after it. All right, let's go on to multiplying and dividing. Multiplying and dividing are a little bit different. You have to have the same index. That's pretty much the only thing. So you can multiply a square root times a square root, a cube root times a cube root, but again, you can't do square root times cube root. That one doesn't work. So when you're multiplying, you're going to multiply the stuff out in front, so your coefficients. So for here, -2 times 3 would give us -6. Multiply your radicands together, so 3 times 6 would give us an 18. And then you simplify. So again, our perfect square that comes out of 18 is 9. Square root of 9 would be a 3 times a -6 would give you -18 radical 2. $15, what's our coefficient on the second radical here? This is a 1, so 4 times 1 would give us 4. X squared times 16x to the 4th. What does that give us? 16x to the 6th. So this one's a cube root. Is 16 a perfect cube? Nope. What is the largest perfect cubes that'll go into it? 8. Is x to the 6th the perfect cube? Yes, because I can divide 6 by 3. So cube root of 8 is 2, but times the 4 makes it an 8. 6 divided by 3 makes it x squared. And then I still have my cube root of 2. So you multiply the stuff outside, multiply the stuff underneath, and then you simplify. $16, if you're squaring just one term, 7 radical 3 is one term. You're going to square the coefficient, so 7 squared is 49. You're going to square the radical, which what is radical 3 squared? Which is 3. And then you just multiply, so 49 times 3 gives us 147. We can do distributive property with our radicals. So 2 radical 5 times radical 5 would be 10, because radical 5 times radical 5 would give you 5, and then times the 2 would make it 10. Plus 2 times the 7 gives me 14, 5 times the 8 gives me radical 40. What is our perfect square that can come out of 40? 8 is not a perfect square, that's a cube. The perfect square that can come out of 40. 4. Square root of 4 is 2 times the 14 that was there is 28. Radicals always go at the end. Just like your eyes always win at the end, radicals always go at the end. $18, distributive property. So 3 times 4, 3 times negative square root of 5. Square root of 5 times 4. Square root of 5 times negative square root of 5 would be negative 5. Because again, radical 5 times itself is just going to be 5. So 12 minus the 5 gives me 7. Negative 3 radical 5 plus 4 radical 5 gives me radical 5. Again, radical is always written last. What should we do for 19? Yeah, you got to do distributive again because it's 2 terms that are squared. So what I like to do on these ones so that I distribute correctly is I like to write it twice because it's the 2 radical 3 plus 1 squared. So I write it a second time, and then you can do your distributive property. So 2 radical 3 times 2 radical 3 would be 4 times 3, so 12. The 4, because 2 times 2 is 4. Radical 3 times radical 3 is 3. 2 radical 3 times 1 would be 2 radical 3. And then distribute my 1. So 13 plus 4 radical 3. Number 20. What are those called? Conjugates. Do you remember the awesome thing about conjugates when you're multiplying? It's easier. What do you have to multiply? Just the first and the last. With conjugates, remember, all you have to do are the first and the last. So 2 times 2 is 4. Negative radical 3 times radical 3 would be negative 3. So we get 1. So now with division, again, if you have ones like number 21 here, separate them out so that your numerator and your denominator are separate. Sometimes I just simply do that in my head, but that's what's happening is you want to separate those out. So then what's the square root of 121? 11. What's the square root of 9? 3. So if they're perfect squares, again, nice and easy, you just take the square roots and you're done. 22 is already separated for us. So what you always want to try to do is see if you can divide the radicands. Can we divide 90 by 18? Try it. 90 divided by 18. 5. So if you can, divide them. That's going to be the easiest way. So I still have the 2, though, because my coefficient on the 18 was a 1. So 2 divided by 1 gave me 2. Divided my radicands. That gave me radical 5. There will be some instances where you cannot simply divide like that, though. So you have to remember, you cannot leave a radical in the denominator. That's not okay. So we have to do the process known as rationalizing the denominator. So taking a look at that first one, I can't divide 7 by 5. I would get a decimal. So I'm going to first rewrite this as the square root of 7 over the square root of 5. And then kind of like what you did with our i's, I'm going to multiply top and bottom by that radical 5 because that's going to get rid of that radical 5 in the denominator. So 7 times 5 gives me a radical 35 in the numerator. Radical 5 times radical 5 gives us 5. And now it is rationalized, meaning there's no radical in your denominator anymore. So then number 24, I can't divide 2 by radical 8. There's 2 ways we could go about it. Some people would simplify the radical 8 first and then rationalize. Or you can rationalize and then simplify. It really doesn't matter which order you use. So we'll go with rationalizing first, so then I only have to simplify once at the end. So 2 radical 8 in the numerator. Radical 8 times radical 8 gives us 8. So then what's our perfect square that comes out of 8? 4. So I get 4 radical 2 in my numerator. Can I reduce the 4 and the 8 now? Yep. So radical 2 over 2. All right. 25, let's check. Can I divide 24 by 2? Yep. Can I divide 2 by 2? So I'm just going to go with my division rules. I don't need to worry about rationalizing here. So 8 divided by 4 gives me 2. 24 divided by 2 gives me 12. 12 divided by 4 gives me 3. Radical 2 divided by radical 2 would give me 1. So it reduces. Perfect square again that comes out of 12 is 4. Square root of 4 is a 2 times the 2 that was already there, makes it a 4 out in front. And again, the radical comes last. So yes, it has to be 3 plus 4, radical 3. '26 and 27 are a little different. Why are they a little different? Because they're cube roots. So our process is a little bit different for our cube roots. So when we go to rationalize our cube roots, what we actually multiply by is the cube root of 54 squared. So the reason why we have to do 54 squared is if we didn't do that and we just had 54, and I tried to do math, choice 4, cube root of 54 times 54, it doesn't work out. So if I only multiply it once and I have the 54 times the 54, it doesn't work. You need to have 54 there 3 times, because then it would end up working out. You would then end up having a perfect cube. So when you go to rationalize with a cube root, whatever your radicand is, that needs to get squared, because then that takes care of the cube part. Then there's going to be 3 of them. It's going to end up working out. So when I do that, I end up with 2 times the cube root of 54 squared all over 54. Because again, 1 cube root times 2 of them over there. Let's actually figure out what's 54 squared. It's a big number. 2,916 over 54. What is our perfect cube that comes out of that number? Oh, it's one of them not on the list, actually. You have to go a little higher. It's going to be 729. So the square root of 729 is 20, or the cube root of 729. Hold on.
It's 4. 9.
Is 9. Yeah. 18 cube root of 4 over 54. Can I reduce 18 over 54? Pretty sure, yeah. What is it? 1/3. So cube root of 4 over 3. A lot more work on those ones. So what would we multiply by for the 27? To rationalize it. Cube root of almost 24 squared. If it's a cube root you're rationalizing it, you've got to do that Radicand squared when you rationalize over there.
It's for every single one too.
For the cube roots.
Only for cube roots?
Only for the cube roots. Not for your square roots. Only the cube roots.
Not for the four.
For the fourth roots, you would have to do the fourth root to the third. Yeah. All right, so let's see here. 24 squared is 576. Let's find our largest perfect cube that will go into 576. Is it 64? God is 64. So cube root of 20 or 64, and then it's the cube root of 9. 4 times 2 is 8. Can we reduce 8 and 24? We sure can. Now don't let that mess with your head, because so many times people see the 3 from the radical and the 9, they're like, you can divide 9 by 3. But you got to remember that means cube root. 9 is not a perfect cube. All right, 28, ones like 28 and on. What do we multiply by when you have a binomial? Conjugate, good. So we would multiply this one times 5 minus radical 3, because that would be your conjugate. You just change that sign in the middle. So in the numerator, I would get 10 minus 2 radical 3 when I multiply. My denominator, we just have to multiply the first, so 5 times 5 is 25. Multiply the last, radical 3 times negative radical 3 would give me negative 3. So in that denominator, it's 25 minus 3, 22. 10, 2, and 22. I can divide those all by 2. So I get 5 minus 1 radical 3 all over 11. It has to be all 3 of those. So that number, the one in front of the radical, and then one in the denominator, they all have to be divisible by the same number to reduce those. $29, what are we going to multiply that one by? 4 plus radical 5. Conjugate of the denominator always. So distributing up top, we get 12 plus 3 radical 5 plus 4 radical 5 plus 5 all over 16 minus 5. So combining our numerator, we get 17 plus 7 radical 5 all over 11, which are all prime numbers, so I can't reduce those anymore. 2 more. What do we multiply by for 30? 2 radical 7 minus radical 2. Even though there's 2 radical signs, your conjugate still happens the same way. You change that sign in the middle. So multiplying, I get 6 radical 14 minus 6, because radical 2 times radical 2 gives you 2, but times the 3 makes it a 6. And then let's see here. 4 times 7, 28 minus 2. So rearranging my order in my numerator, because radical has to go last. So negative 6 plus 6 radical 14 all over 26. I can reduce the 6, and the 26 by what? 2. So negative 3 plus 3 radical 14 all over 13. All right, one more. So multiply top and bottom by 4 radical 3 plus 6. Give you a minute. Go ahead and try that one.